Hello, in this video we will go over orthogonal sets of linear algebra. So linear algebra orthogonal set. So you're probably thinking, what is a orthogonal set? So we know that a sective vector can be expressed as this, u1, u2, up, and Rn is called an orthogonal set if the dot product of ui times uj is equal to 0. So you remember, I think in the previous video, we said orthogonal is the same thing as perpendicular. And if you multiply the two vectors out, it gives you a 0, right? Okay, so that's how it is in linear algebra. So let's do an example. So example, is these three vectors, u1, u2, and u3 an orthogonal set? If so, show that if so, show that if is row equivalent to I3 base basis for 3D. So what you have to do is do a few things in order for it to prove that it's orthogonal. First, you must prove that the dot product of u1 and u2 is 0, and then the dot product of u1 and u3 is 0, and then the dot product of u2 and u3 equals 0. If all three are true, then it is orthogonal. If none to one, then it's not orthogonal. So if it fails one, then it's no longer orthogonal. So I kind of did this one ahead. So here's the three vectors. If you do the dot product of u1 and u2, it does come out to be 0. And if you do the dot product of u1 and u3, it also becomes 0. And then if you do the dot product of u2 and u3, it also becomes 0. So this proves that it is orthogonal. So yeah, is this an orthogonal set? Yes. And then if they said if so, what you have to do is row reduce. So we were given our three vectors right above here. Or was it? Yeah, 1, -1, 1, 1, 0, 0, 0, 1, and then you just augment it. You just row reduce, right? And then this is how you get this matrix. Okay, let's talk about some theorems. So theorems, suppose that S equals this vector is an orthogonal set of a non-zero vector in Rn, where W equals the span of this vector. Then S is linearly independent and a basis for W. An orthogonal basis for a subspace, an orthogonal basis for a subspace W of Rn is a basis for W that is also an orthogonal set. If S equals this is an orthogonal basis for a subspace of W of Rn and Y is in W, then Y has a unique representation as a linear combination. So let me rewrite go over this theorem. It says an orthogonal basis for a subspace W of Rn is a basis for W that is also an orthogonal set. If S equals this vector is an orthogonal basis for a subspace W of Rn and Y is in W, then Y has a unique representation as a linear combination. So C1 equals this, C2 equals that, and CP equals that, which equals to Y equals this. So C1 is Y times U1 over U1 times U1. C2 is Y times vector 2 or U2 times U2 times U2, and then etc. So maybe if we do an example. So here, this example says, oops, I can't go up a bit. So this example says, express the vector y equals 374 as a linear combination of the orthogonal bases of these three vectors, u1, u2, and u3. So we got to express it as a linear combination of the orthogonal basis of those three vectors. So how do we do this one? So what we're going to do is first we're going to find C1 and C2 and C3, right? So here, go ahead and write these down. This is my vector U1, my vector U2, and my vector U3, and then this is y equals 3, 7, 4. So yeah, go ahead and if you need to pause, go ahead and pause because I need to find C1, C2. I already have it on my notes, so I'm going to just start with C1. So C1 is equal to y times U1 over U1 times U1. So I already know the vector, so it's like, so on the top, y times U1 is the same thing as 3 times 1 plus 7 times -1 plus 4 times 0, right? All over U1 times U1 is the same thing as 1 square plus -1 square plus a 0 square. And when you put it all together, on the top you get -4 over 2, and then -4 over 2 is -2. Okay, now let's do C2. So C2 is y times U2 over U2 times U2. So I already have the vector in my notes. So on the top, y times U2 is 3 times 1 plus, so wait, I'm doing the dot product. Um, plus 7 times 1 plus 4 times 0. Okay, and then all over U2 over U2. So U2 is 1 square plus 1 square plus 0 square, right? So on the top, when you do the algebra, you should get 10, and then on the bottom, you should get 2, just 5. Okay, let's move on to C3. So C3 is y times U3 over U3 times U3. So that's going to equal to 3 times 0 plus 7 times 0 plus 4 times 1 all over 0 square plus 0 square plus 1 square. So on the top, when you do the algebra, you get 4, and on the bottom, you get 1. 4 over 1 is 4. Okay, so I found my C1, my C2, and my C3 from using the formula that was given. So let's find the last part. It says express it as a linear combination. So basically they want you to solve put it in y equals. So y equals C1 times U1 plus C2 of U2 plus C3 times U3. So we already have our C1, our C2, and our C3, right? It's the one above, right? C1 is -2, C2 is 5, and C3 is 4. No biggie, right? We don't really know what U1, U2, and U3 is, so we'll just leave it as U1, U2, and U3. So my final answer will be -2 U1 plus C2 is 5, so it's 5 U2 plus C3, which is 4 U3. Okay, so this is my final answer. Okay. The next thing we're going to have to learn about is orthogonal projection. So, yeah, let's talk about orthogonal projections. So, orthogonal projections for a non-zero vector u in Rn. Suppose we want to write y in Rn as the following. y equals a multiple, whoops, y equals the multiple of vector u plus the multiple of vector perpendicular to vector u. So what we're doing is, here's a little image. Here's vector u, here's vector y, and then this is magnitude of vector z. So vector y casts a shadow onto vector u. So this is vector u, yeah, and then this is the magnitude of z, and then this is vector y. So vector y, it casts a shadow onto vector u. So vector u is the projection of u of vector y, and then vector y is equal to y minus hat. So just go ahead and copy this down because z is y minus vector y, or z equals y minus y times u times vector u over u times u, basically the component of y orthogonal to u. So let's do an example to make this theorem more clear. So in this example, it says compute the orthogonal projection of this vector 1, -1 onto the line of -1 to 3 and the origin. And then so yeah, compute the orthogonal projection of vector 1, -1 onto the line of -1 to 3 and the origin. So we know that the projection, or we know that the orthogonal projection is y hat. So y hat, so we know that this little like this, yeah, means y hat is equal to y times u all over u times u. So right here, let's do the numerator. What's the dot product of y times u? So um we have the y and the u. I think this is our y and this is our u. Yes, this is our y, this is our u. That is going to be so what is the dot product of y times u? It is going to be 1 times -1 plus -1 times 3 all over u times u. So vector u is th this one. So that's going to be -1 square plus 3 square. And don't forget, we still have to times this by vector u. So my vector u was -1 and 3. Okay. So if we kind of clean it up a bit, it's going to look like this. Oops. We know it's going to be y hat equals to, I guess if you clean this up, -1, this will give you -4 on the top. And then on the bottom, it gives you 10. We got to still times it by vector u, which is -1 and 3, right? And I guess what you could do is -4/10 can be reduced by 2, so that's like -2/5 times it by -1 and 3. And then when you multiply that out, you get 2/5 and -6/5, right? So y hat as my final answer will be this vector, 2/5 and -6/5. I think, is that our final answer? Yes, that is my final answer. So this is our projection, or our orthogonal projection, or y hat. Okay. Let's move on to the next example. These aren't too bad. You just use the formulas, and then yeah, these aren't too bad right now. So let's do another example. This example says let y equals the vector -8, 8 and 4, and u is the vector 3, 1. Compute the distance of y to the line through vector O and vector u. So compute the distance. So our final, when they say distance, they mean find the magnitude, right? So if I kind of draw like an image, right? We're given vector u, we're also given vector y. So what we're trying to do is graphically this is y hat. This is the magnitude of z. That's what we're trying to find, the distance. Magnitude of z, and then this is vector y. So what we know is if we want to find y hat, we need to find y hat in order to find z because z is the same thing as y minus y hat, vector y minus y hat. So how to find y hat? Y hat is y, vector y times u, times u, times u, times by vector u. So when you do that, you get right here, what's what? The dot product of y and u. It is -8 times 3 plus 4 times 1 all over 3 square plus 1 square. And then times it by vector u, which is 3 and 1. Okay, so when you do the algebra, uh, -8 times 3 plus 4 times 1, that's -20. 3 square plus 1 square is 10. Times it by vector u, which is 3, 1. Uh, let's see, -20 over 10, that could be, the 10 can be reduced. So it's really -2 times by 3 and 1, which is -6, -2. Okay. So we need that and we need that to find z because we're trying to find the distance, this part, the magnitude of z. So z is equal to y minus y hat is equal to, so we know vector y is given, which was -8 and 4, minus y hat, which we just found, which is -6 and -2. And when you do that algebra, so -8 minus a -6 is positive. I mean, -2, right? Two negatives becomes a positive. -8 plus 6 is -2. And then 4 minus a -2 is +6. Okay, so we found z. Now let's find the distance or the magnitude. How do you find the magnitude of z? Basically, it's the square root of -2 squared plus 6 squared, which is -2 squared is 4, 6 squared is 36, which is square root of 40. I guess you could simplify that, or you could just leave it as it is. So 40 could be simplified as 10 and 4, 4 is 2 and 2, 10 is 5 and 2. So the magnitude of z, you could say square root of 40, or you could say 2 square root of 10. Okay, so we found the distance. This isn't my final answer. This or this. Okay, let's move on to the next example. So this example says, look, vector y equals 2 and 2, 6, and vector u is 7, 1. Write y as a sum of vectors in the span of u and a vector orthogonal to u. What does that mean? So basically, we want to find y. So let's use what we know. What we know is, whoops, go ahead and copy that down if you need to, or press pause. We know that y hat is equal to y times u over u times u times vector u, right? We know that. And we also know that z is equal to y minus y hat, right? But what we want is y, just y by itself. So in order to get y, we'd have to add y hat to both sides. So that would be y equals z plus y hat. So that's what we need to find. So let's do the work. So first let's find, we should find y hat. Okay, so go ahead. This is our y and that's our y vector and our u vector. So let's go ahead and find y hat. So y hat is going to equal to y times u over u times u times vector u. And that gives you 2 times 7 plus 6 times 1 all over u times u. So that's 7 squared plus 1 squared. And then we still got to multiply by vector u, which is 7 and 1. So y hat is going to give you, on the top, when you do the algebra, you get 20 or 50 divided by vector u, which is 7 and 1. And what happens is 0 cancels. So you're left with 14 fifths and 2 fifths. So we found y hat. Now we can find z. Now we got to find z, right? So z is this, y minus y hat. So z is y minus y hat, which equals to y is 2, 6 minus y hat, which is 14 fifths and 2 fifths. And when you do the algebra, this is what you're going to get. It's really saying 2 minus 14 fifths, and then 6 minus 2 fifths equals to 10 fifths, negative 14 fifteenths, 30 over 5, and negative 2 fifths. Okay, and then when you simplify this, you're going to get negative 4 fifths and 28 fifths. So what we need, this is z, so we need to find y. So y is equal to vector z, which is this one, plus y hat. So that's going to be negative 4 fifths, 28 fifths, plus y hat, which is 14 fifths, and 2 fifths. And you can just leave it like that. So this is your final answer. Not too bad, right? Just use the formula and then plugging it in. Let's go over one more theorem or a few more theorems and then one last example. Okay, so the next one is orthogonal sets. So let's quickly talk about that. So not orthogonal, orthonormal sets. That's what I meant. Orthonormal sets is a set of vector where U1, U2, and UP in Rn is called an orthonormal set if it is an orthogonal set of unit vector. If W equals span of U1, U2, and UP, and U1, U2, and UP is orthonormal basis for W, it must be orthogonal. All the dot product must equal 0 and must be orthonormal, meaning their length must equal to 1. So in order, it needs to satisfy two things. It must be orthogonal, meaning the dot product is equal to 0, and must be orthonormal. That means their length or their magnitude is 1. So if you recall the magnitude of V, so the magnitude of V is the same thing as square root of vector V times vector V, or you could think of it as a square root of vector V transpose times vector V. And then the unit vector is vector V all over the magnitude of vector V. So let's go over a theorem. So a theorem says an n by n matrix U has an orthonormal columns if and only if U transpose times U equals to I, or is the same thing as U inverse is equal to U transpose if orthonormal. And then another theorem says let U be an n by n matrix with orthonormal columns and let vector x and vector y be in Rn. Then you got to satisfy these conditions. Condition A, the magnitude of U vector x is equal to the magnitude of vector x. Um, part B, U times vector x times U times vector y is equal to vector x times vector x times vector y. Part C, U times vector x times U times vector y is equal to 0 if and only if vector x times vector y is equal to 0. So the magnitude of U is the same thing as square root of U times square root of U times U is equal to 1. So go ahead and copy all that. Yeah, let's do the last example. So this example says determine which sets are orthonormal. If a set is only orthogonal, normalize a vector to produce an orthonormal set. So let's look at part A. We have these two vectors, vector u and vector v. They're almost the same. The only difference is one's like the negative. Right? Vector u is this vector, and vector v is this. Almost identical, right? So, um, the first part says determine which sets are orthonormal. If a set is only orthogonal, normalize the vector to produce an orthonormal set. So what we got to do is first we got to determine if it's orthonormal. So that means is we got to do vector u times vector v gives you 0. So is that true? Let's see. That would be negative 0.6 times 0.6 plus 0.8 times 0.8 times 0.8. And that gives me negative 0.36 plus 0.64, and that gives me 0.28, which does not equal to 0, so it's not orthonormal. Okay, let's do part B. Part B says we have this vector u and vector v, so let's determine if it's orthonormal. So let's see if their dot product vector u times vector v gives you dot product of 0. So let's see. So it would be 8 times -6 plus 6 times 8. That gives you -48 plus 48. It does give you 0. So yes, it is orthonormal. I mean, not orthonormal, orthogonal. So the next part says if it is orthogonal, we got it, is this normal? So what that means is vector u, the magnitude of vector u must give you 1. So is that true? The magnitude of vector u should give you 1. So is that true? So that's going to be square root of 8 squared plus 6 squared equals square root of 100 equals to 10. It does not equal to 1, right? 10 does not equal to 1. What about vector v? So the magnitude of vector v is -6 squared plus 8 squared. That gives me a square root of 100, which is also 10, which is not equal to 1. So that means that it would be orthonormal if it would be orthonormal if 810 and 610, if these were your vectors, right? So yeah, it would be orthonormal if the first vector was 8, 10, 6, 10, and the second one is -6 tenths and 8 over 10. So what we did was basically vector u over the magnitude of u, which we found was 10, right? Magnitude of u was 10. And then for the v, it was vector v over the magnitude of v. So if it's not orthonormal, you can make it orthonormal by just using this formula. Okay, last question, and then we are done. So vector C, letter C, we have this vector u and then this vector v. Okay, so first we got to determine if it's orthogonal. So let's see. So that means that vector u times the dot product of vector v gives you 0. So is that true? So vector, it's going to be -2/3 times 1/3 plus 1/3 times 2/3. Uh, does that give you 0? I think so, because, and then this is continue 3 by 3, so it's going to be 2/3 times 0. So does this give you 0? So this is going to be -2/9 plus 2/9 plus 0. Yeah, right. That gives you 0, 0. So yes, 0 equals to 0. So We know, yes, orthogonal. But are they orthonormal? How do we determine if it's orthonormal? The magnitude should give you one. So let's start with vector u. So the magnitude of vector u is square root of negative 2 third square plus 1 third square plus 2 thirds square. And that gives you square root of 4 ninths plus 1 ninths plus 4 ninths, which is the square root of 9 over 9, which is 1. Hey, yeah, that sounds true, right? If it gives you a magnitude of 1, that means they are orthogonal. So for vector u, it would be yes. What about vector v? So vector v, does it give you a magnitude of 1? Let's see. It would be the square root of 1 third square plus 2 thirds square plus 0 square, which gives you the square root of 1 ninth plus 4 ninths plus 0, which gives you square root of 5 ninths, which does not equal to 1. So we need to fix this. How do we fix this? Mm, How do we make this orthonormal? So square root of 5 ninths is the same thing as square root of 5 ninths is the same thing as square root of 5 over 3. So the vec define yeah, the magnitude of v is square root of 5 over 3. To fix this, we must set it up as vector v over the magnitude of vector v. So that would be, it's a confusing one. It would be equal to 1/3 over square root of 5 over 3. And then it would be 2/3 over the square root of 5 over 3. And then it would be 0 over square root of 5 over 3. And when you clean this up, you're going to get this. 1 over square root of 5, 2 square root of 5, and then 0. So this would be our fixed vector. So our orthonormal set is this. Negative 2/3, 1/3, and 2/3. And then for the vector v would be one, when you simplify it, it's 1 over square root of 5, 2 over square root of 5, and then 0. So that would be our orthonormal set for vector u and vector v. Okay. Okay, so we went over orthogonal and orthonormal sets, so I'm going to stop right here, and then we'll talk about the next video should be about orthogonal projection and decomposition. Okay, I'm going to stop here.